Hi there guys, well we're working towards 3.0 now, and 3.0 in the HLAA Oxford book is about solving polynomial inequalities. Okay, so we're going to look at some algebraic techniques here through the questions by, again, factorizing and then considering signs, or maybe considering how to sketch the graph out. They come up with these sign tables here, which I wouldn't want to be doing that in an exam. And then there's a lot of calculator methods here as well. So I'll go quite quickly through the calculator methods, just sort of give a couple of hints. Okay, so example 34. And again, we're dealing with questions here which don't have complex roots, or possibly some of them could have complex roots, but we're just talking about solving this in the real domain. Okay, the question is not talking about this in terms of any complex domain. Okay, so let's take example 34. It says use an algebraic method to solve this inequality here. So when we're seeing an algebraic method, we're thinking this probably factorizes. I'm expecting it to factorize. Otherwise, I'm not sure how I'm going to do this via an algebraic method because I can't use the cubic formula. Okay, so the book is using the method again where they're splitting up the linear term, and I'm not going to do that, but we'll have a look at that once I've finished my method. So I'm going to start off by looking for some factors, and a little tip here, which was mentioned in a previous exercise, is that if you can spot that your coefficients are 1, 4, 1, and -6, and that when you add them together here, that gives you 0. That means that when you put in x is equal to 1, it's just going to give you out those answers, and when we add them all together, it will give 0 as well, meaning to say that we have a factor which is x minus 1, or our root is equal to 1. So that's a bit lucky, but of course, sooner or later, if we try plus or minus 1, plus or minus 2, plus or minus 3, just looking at the factors of -6 here, and plus or minus 6, sooner or later, we're going to find a factor, and sooner rather than later, really. Okay, so it turns out that putting 1 in is a factor. So now we can divide this thing by 1. Now, I prefer the method of the algebraic long division method. But let's try the synthetic division again here, and we've got 1, 4, 1, and -6. And we're talking about dividing by x minus 1. So we're putting 1 in, bringing the 1 down, we're putting plus in front of these things here. We've got the 1 there. 1 times 1 is 1. 4 plus 1 is 5. 5 times 1 is 5. Plus those together gives us 6. Times by the 1. 6 times by the 1 is 6, and then add them together gives us 0, which we're happy about because we know that this is a fact. Okay, and of course this one just gives us straight away our quotient. We don't have to worry about there being another number involved here. We're not dividing by 2x minus 1, so we're not having to adjust these numbers at all by dividing them by 2. Now, so our quotient in this case is going to be x squared plus 5x plus 6. And that's now our f of x, if you like, this function here. And we're still asking, when is this greater than 0? Okay, so just to take this a little bit further, we can clearly see how this factorizes again. We've got x minus 1, and we can see that we've got a plus 2 and a plus 3 there. And we're asking again, when is this greater than 0? Okay. Now, from my point of view in this case, I think we have a cubic. We have a cubic which looks like this, a positive cubic. Negative cubics look like this. And cubics without any other terms other than the x cubed term will look like this, or will look like this. Okay, they won't have those extra 2 turns, if you like, the 2 extrema. So we know this is looking like this. We know on the axis as well that our roots can be plotted as 3 minus 3, sorry, minus 2, and at 1, we know the graph goes like, let's just go straight through that, goes like this somehow. Okay, we even know that it crosses the y-axis at minus 6, so that helps us verify the fact that this is going to be a negative answer there, and this section here definitely has to be below the axis. Now we're asking, when is this above the axis? When is this f of x, which I've drawn here? There's my f of x that I've plotted. We're saying, when is f of x greater than 0? Well, it's greater than 0 here and here. And in terms of the x values that makes that so, that's between minus 3 and minus 2 and greater than 1. So we can say that this implies that we're having our sets of x numbers which solve this inequality between minus 3 and minus 2, comma, x is bigger than 1. And that's what I would do for this question. Now, the book has treated this quite differently, in fact. And I think that my method there is pretty quick. I've explained it at the same time, but you can see that can be done in a couple of minutes once you get quick at that. Now, if you have a look at the way the book has done this one, the book has done this factorization. Just steal this. Let's just copy this bit here. It's done this factorization through splitting the middle term again. And again, I find this difficult myself. So they're talking about splitting this term. Now, previously, we could see that we could solve that puzzle. We could say two things times together to give you minus 6, and they add together to give you our plus 1. Okay, now we're still trying to go with that, and we're saying, well, okay, well, we can see that the two numbers, yeah, that's where I get lost, to be honest, because in fact, that doesn't work in this case, because when we're splitting this up, we're splitting this up into 4 and minus 3. Now, maybe I'm missing something here. Maybe I'm missing some bit of teaching from further back, but I just don't see how this is easily done. Because you could split x up in different ways. You could say, well, I don't know, maybe I can see I've got to join this with I've got to have a factorization on this side that's going to give me a similar factor to the factorization on the other side. Well, who's to say that this doesn't split up in terms of minus 2x and 6? And then if you've got minus 2x there, maybe to get the x, we can see that we've got 3x there. And so now we've got x cubed and 4x squared and 3x, and we're going to have to factorize that. And then you see that you can't do that. Maybe you can. Maybe that does work. But I'm just, for myself, there's too much doubt in my mind that I'm not going to get this. And from my point of view, it's really quick to check through a few factors to find your first factor, and that's my approach. Let's just see if we can take that one forward a little bit there. I'm kind of intrigued by this now. And let's put that plus 3x. And we've got there, what do we say, minus 2x and minus 6. So let's see if we can take this forward. So I can see I've got x and x squared plus 4x plus 3 there. And we've also got here minus 2, and then we've got x plus 3 in there. Can we factorize out an x plus 3 from this? So the x plus 3 and x plus 1, well, now that does work. Okay, now that does work in that case. And now I'm not finding a case which is disproving this at the moment. And then we could factorize out x plus 3. So we can see that that is working, in fact, in a different way to the way in which they're doing it in the book there. Now, let's see if we can split it up even further, okay? So what happens is, let's test this one out. What happens with this plus x? If we say here, okay, well, maybe to share a factor with the minus 6, let's put in there, let's say, for example, let's put in a 6x minus 6. Now, I can see that I'm going to be able to factorize out an x plus 1 there. I'm sort of looking at my answer there. So if I put this one as a plus, 6. Then I'd need to put in, by splitting this term of x, I'd need to put in a minus 5x there. And so here we've got x cubed plus 4x squared. And so there would be our rewriting of this thing here. And then we could see, well, if we take out an x here, we're getting x squared 4x minus 5 plus 6 lots of x minus 1. Well, that's working. Okay, and let's see if we can take that forward. We've got x minus 1 there and x plus 5. Well, that is working. Is that working? And x plus 5. We're getting the x there. And let's see if we just take that one further. I think that's going to actually take us further as well. So that is working again, I think. We've got x minus 1 as factors x plus 5. And we've got plus 6 there. And if we multiply that out and then factorize it again, we'll get our other two factors. So all of that is working just at the moment. Now, I'm just trying to find a case where it doesn't work. So where we have, let's say, for example, we take 6 minus 6x minus 6 there. And then, so we're talking about that x. And then we've got 7x there. Okay, and now this time around, we're not going to get one of these factors when we factorize out this thing here. So this one shouldn't work. Okay, so there are cases which do work and there are cases which don't work. And it's that uncertainty which bothers me for that approach. And so then we try and factorize this one. We're getting x squared plus 4x plus 7. And now you can see that you can't factorize this. There are not two numbers which times together to give you 7 and which add together to give you plus 4. Okay, now I'm going on a bit about that, but you might like this method. You might like, now you've seen that, to try and get some practice doing this. For myself, I would just try plus or minus 1, plus or minus 3, and plus or minus 6 as roots by substituting those in for f of x. Okay. Right, let's have a look back at the book then. Now, they also come up with this method here, and I have to say the sign table for me is, that's looking quite confusing. And again, for me in this situation, what I would do is we're saying if this has got to be greater than 0, and if the book asked for a sign table, it's fine. You can still, sorry, the exam asked for a sign table, that's absolutely fine. You can still do that by just coming up with your line, and you come up with minus 2 and 1, minus 3, minus 2 and 1 as your roots. And then you can just think about what's happening in each of these sections. And that's essentially your sign table. Now, you can definitely say what's happening, set it up a bit more formally. You can say what's happening when x is less than minus 3. And then you can say, well, what's happening when x is between minus 3 and minus 2, and so on. You can come up with your other two inequalities there and just say whether or not we're getting positive or negative in that. Okay, so you can make a table sort of slightly more formalized there. However, what I would do is just test a number in each of these sections. Because this graph is continuous, it's not possible that you could have, say, for example, we have a positive number here when we try a number between minus 3 and minus 2. And it's not possible to then go underneath the axis again, because otherwise there'd be another root. So it's not possible to get a negative in that section as well. You're only going to get all positive or all negative. Okay, so let's just think about what we're getting. Let's try a number here. So let's try f of 0. We can see that easily gives us out minus 6. So we know that this is going to be negative in here because that's where 0 is. And we're getting an answer of minus 6. We know that that's true. Now we should really know what the shape of x cubed is like as well. But let's check the other ones as well, because I suppose it's possible that at some stage we could have a repeated root. So it's possible that you could get a negative on both of those sides there. Now, simply because we've got three roots there, we know that that's not true. But okay, you know, it's just playing devil's advocate a bit here. So let's try a number which is greater than 1. So let's try f of 2. And f of 2 in this case is going to give us f of 2 is going to give us putting in 2 into this function here. So we're going to get 8 plus 16 plus 2 minus 6. We don't really need to calculate that because we can clearly see that that's positive. Okay, you can just say, well, that's bigger than 0. And then likewise, you can do the number which is less than minus 3. So you could say minus 4. And again, minus 4 cubed is going to dominate this thing here. So again, minus 4 cubed is 256. So that's minus 256 there. No, it's not. Sorry, that's to the power of 4. It's minus 64. And then plus 4 lots of 16, which is plus 64. And then you've got plus 4 and minus 6. It's giving us minus 2, which is less than 0. So we can see here we're also getting a negative. And I mean, obviously, you can check minus 2.5 as well. Okay, so you can make up your sign table pretty quickly here as well. Personally, I would just go with the shape of the graph. Okay, if you are going with the shape of the graph, just remember if you've got repeated roots, say for example we have x minus 1 squared and x plus 3, remember how that's going to look. We're going to have a repeated root at x plus 1. We'll have a root at x minus 3 as well. And it still has this positive quadratic shape because the leading term is x cubed. So it's either going to go like this, or it's going to go like this. Now, because the repeated root is here, it has to go like this. So if you had something like this, you just need to be careful about how you sketch your graph in this situation. Okay, so let's look a little further. Where do we get to now? You see as well, they're giving us their answers. They're giving in this format. Remember, you only need to read this format. This is saying that, first of all, x is between, but not including, minus 3 and minus 2, not including because the bracket turns away from the two numbers. And for the next one, so we're saying or, not and, or, because it's union, we're saying as well that x can be greater than 4, okay, up to infinity, but it can't be equal to 4 as well. Okay, so that's a perfectly fine way of coming up with your answers to this question. Okay, and they're saying as well, how do you do this with a graph? Well, there we go. With the GDC, you could draw the graph, and you could just take the sections which are above the graph. Okay, example 35. We might rush through these ones a little bit now. So example 35 says, given the polynomials, we've got two polynomials here, find all of the values such that f of x is greater than g of x by using a graphical method on the calculator. Now you've got two options there. You can either draw one function and then draw the other function, and I don't know what that looks like, but let's just say it looks like this. Okay, let's say it looks like, okay, so it looks like that. Okay, we could draw the two functions, and as long as we've labeled, we know which one f of x is and we know which one g of x is, then we can say, okay, where is f of x bigger than g of x? Well, it gives answers which are greater when our line is above the g of x line. So it will be between the two solutions here and here, and above this solution here. Okay, which is the same as solving a single cubic by rearranging this by taking everything over to the other side. So making one cubic greater than or equal to 0. So we've got the two options there. Now, if you do this method here, you're going to need to draw two graphs, and you're going to need to find each of those solutions by coming up with, looking for your solution on your GDC by coming up with solutions within a particular range. So we need to find the x values where they cross, not where it crosses the x-axis. Okay, for myself, I would probably rearrange this because I would say this question is the same as doing 3x cubed. So we've got plus 2, let's just write that to start off with, greater than or equal to x cubed minus x squared plus 3x minus 1. Take everything over to the left-hand side here. So we've got a positive amount of x cubed. So we've got 2x cubed. We've got plus 3x squared. We've got minus 3x. And we have minus 2 then. We're asking when is that greater than or equal to 0? Now, again, this might factorize, but I suspect by the fact that they're talking about using a graphical method, that in fact it doesn't factorize in this case. So, so now plot this one on your graph and then just find out, it's positive cubic, find out when we're above the axis. So between these two and above this one here. Okay, so that's what you would do, and you'd be allowed to equal it to those two solutions there as well, two roots, and you'd be allowed to equal it to this, so it'd be greater than or equal to X3. Okay, there's calling that one X3. Okay, so there's that one, and you can see how they've done that in the book. And in fact, they do cross at whole number points or fractional points. So this one would have factorized. Okay, so you could try this one with factorization. Now, there's a nice little hint here in the book, and it just talks about the fact that if it's not clear on your graph, you might need to zoom in or zoom out. And if you go into your graph, if you analyze the graph, you go into the menu and you go to window and zoom, one of the things you can do is zoom and fit. But what you need to be really careful of is that sometimes when you do zoom and fit, it will say up here something like 5 times 10 to the 8, which is 500 million there. Okay, so you've got to be really careful about what's on the axes here. And so from my point of view, I would probably just want to put this in a sort of region which is going to work by putting in something like up to 100 there and down to minus 100 and maybe up to 10 and then down to minus 10. Because of course, x cubed gets large really quickly. So just take a window which you can then zoom into. Okay, and it still might look like these two things are really, really close together. I don't know. But just keep zooming in or keep zooming out until you've got, something which is looking sensible, which is giving you something really clear where you can find, your solutions and where they're kind of close together. Now, as I was saying here, so where those solutions are sort of pushed apart rather. So now when we're looking here, when I chose those numbers, again, often you'll choose much bigger numbers for this axis, but we just don't want them to be astronomically huge. Okay, so that's a nice little hint. And example 36, example 37 before we get to the exercise. So example 36, again, is just asking us to come up with a simple polynomial graph. And you can see how this one is working. They're just, well, in this case, they're actually splitting it into two graphs. And for myself, I just really wouldn't do that. I would just take the original graph here. So take the x cubed minus x squared. I just take this, plot this, and find out when is that cubic. I don't know what it's looking like, but when is this cubic here underneath the axis? Okay, because it's saying when is this less than or equal to 0? So here and here. So you should get something like this. Okay, and it's allowed to be equal to those points there as well. Okay, now I do it like that, but you can see that in the book they're saying this is equivalent to taking across the x squared and the plus 4. And that's fine. If you want to do that, you can do. And it's just going to create two graphs, and you can see that that's exactly what they've done in the book as well. They created the two graphs there. Okay. Right, and example 37. Again, let's just do this one quickly. So it says use the GDC to solve this inequality here. Again, they've taken everything to one side Personally, I would keep the higher power positive. So I would say 2x to the 7 minus 4x squared plus 1. And we're asking, when is that greater than 0? So that's what I'd be doing. They've just done it the other way around, but it's fine. You can work either way around. It's not going to matter. It will still give you the same solution set at the end. Okay, well, that's that. And now you've got the exercise 3O to do. 4 questions there. Have a go at those questions. Thanks for listening, and hopefully see you back here next time.